So now, so up to this point, we have been computing various correlators, first in position space, then in moment, then in frequency space. So in this lecture, we would like to understand some underlying physics, some physical interpretation for this of these correlators and what do they mean. Okay, and the first clue for this is, for example, consider the 2-point function, the propagator, the Feynman propagator. Feynman propagator in frequency space. Okay, just for simplicity, we restrict still ourselves to 0 plus 1 dimension again, but this holds also in 3 plus 1 dimension. So the expression for the Feynman propagator in frequency space is I h bar e squared minus m squared plus I epsilon. So we already discussed, so note that the propagator has pole, at e square equal to m square minus I epsilon. Okay, so we can always we can Fourier transform it back and go to position space. We have already done those things, but the important thing to note here is that the existence of the pole. Okay, now as we will discuss here, first for 2-point function and then general for arbitrary higher point functions, that this analytic structure, the poles, let's put the slogan, the analytic structure in the frequency space, the analytic structure in frequency space knows about the spectrum. Okay, so this part of the discussion actually is true for any theory, not just necessarily free theory. Of course, we can always go back to free theory and simplify things, but let's just discuss this thing. So the first thing we will discuss is known as Callan-Lemon spectral representation. Okay, so the Callan-Lemon spectral representation basically deals with, so it deals with 2-point function of identical operators. Okay, so let's just for sake of generality, let's just do this thing. For some two arbitrary operators, OT1, OT2, 0. Okay, now the first so now what we do first is that let's insert a complete set of states here. So which means this becomes 0, okay. Now what do we do is that we put the expression for these operators. So this is in Heisenberg picture, and put the expression for these operators in terms of the Heisenberg picture evolution. So this becomes then n 0 exponential minus not minus plus I h by h bar t1 o at 0 n sorry exponential minus I h by h bar t1 n, and similarly there is n exponential I capital H by small h bar t2 0 exponential minus I h by h bar t2 0. Okay, so then I mean this expression can be easily simplified because we know the, let's say we know the spectrum of the theory. So then this expression can be simplified as in this way: n 0 o at time 0 n mod square and then exponential minus I by h bar e n minus e 0 and then t1 minus t2. Okay, so this is for the Weitmann propagator. So let's say if instead of Weitmann propagator, let's say if we had taken the time ordered propagator. So if I take the time ordered 2-point function, then following the same trick we can easily show that this thing will be, all the part will be same, just there will be just modulus sign here. So modulus sign in this place. Okay, so in this case then the expression will be mod square exponential minus I by h bar e n minus e 0 modulus t1 minus t2. Okay, so given this, then let's just Fourier transform. So let's say dt1 minus t2, we just Fourier transform with respect to the difference coordinate. Then this thing simply becomes, so there is a two term 0 o at 0 and then 0 mod square delta omega. I mean this delta function basically comes because when we take this state to be 0, then this is completely vanishing, right? Oh sorry, I forgot to put the usual, the phase factor. So when we choose 0, this is just a delta function. So this is very important that this is a delta function. And then rest of it is sum over n equal to 1 to infinity rho n plus I epsilon. Okay, where rho n is given by, so rho n is simply this quantity. So rho n actually depends on the operator. So rho n is simply 2 times E n minus E0 by h bar n O0 0 mod square. Okay, so this part simply comes from just as we this part simply comes from when we, it's very similar, this part is very similar to when we inverse Fourier, Fourier transform the position space Feynman propagator to momentum frequency space Feynman propagator. This part is same. And then you see that the 2-point function, the momentum space, the frequency space 2-point function has an interesting structure. So that we see that the frequency space two-point function has a interesting analytic structure. How? So firstly, there is a delta function in frequency space. So firstly, there is a delta function at omega equal to 0, and the coefficient of the delta function, is simply the vacuum expectation value. Okay, so it is the vacuum actually mod square of the vacuum expectation value of that operator. Okay, then there is a second piece here. So then there is a second piece here, which says that there is a series of pole at omega square equal to En minus E0 whole square minus I epsilon. Okay, so there is a series of pole, and you see that the series of pole are basically, the poles, you see the poles know about the spectrum. The poles know about the spectrum because the poles are all at En minus E0, so minus I epsilon square. Okay, not only that there are poles, the residue at the pole is also fixed. The residue at this pole is rho n 0. To be more precise, the residue actually also has IH bar square and all this thing. The residue is not exactly this, but it will be controlled by this, because in order to find the residue we have to split into two poles and everything. But the residue is also fixed, and it is given in terms of 2 En minus E0 by H bar N 0 0 0 mod square. Okay, so this is very interesting. This basically says that if we, what this basically means, it means that if we compute frequency space 2-point function of identical operators, then the pole in the frequency space. Knows about the spectrum. Knows about the spectrum, let's put it in this way. The frequency space depends on the spectrum. Okay. And the more precise statement is that depends on the spectrum. And in order to know, then it means that in order to know the spectrum, if we just compute all possible 2-point functions, then basically whether there is a pole or not, that will be controlled by this rho n, right? Now it is possible for some values of n, this quantity vanishes. So in that case, there will be no poles. Okay. So in general, if we compute the 2-point function of any two identical operators, it will have a series of poles, but it will not have infinite number of poles, because in order to have infinite number of poles, we have that will be controlled by this operator, and usually that's not the case. Okay. So in order to do this, that in the lecture note you can find it, you can check, and it's given in the lecture note. Two-point function of, let's say, phi power L or L plus 1 T1 phi power L plus 1 T2, and again then if we do the frequency space, so this is explicitly given in the note, and you will see that this exactly, if we just compute it in the free theory. So in the free theory, then you can explicitly see the structure. You can explicitly see the structure. Okay. We also did another, in the lecture note we also gave another example, so we encourage you to actually check that, and also to do some computation for yourself. But bottom line is that the pole in the frequency space actually knows about the spectrum. So if we compute a 2-point function and it in the frequency space, and the pole will know about the spectrum. But this structure, it doesn't stop at 2-point function. So Callan-Lemon spectral representation. So this form is actually known as, sorry, I should have said. So this form is known as Callan-Lemon spectral representation. So Callan-Lemon spectral representation is for 2-point function of identical operators. What about more general correlation function? For example, what about if we just take let's just take more general operators. And let's say we also take Fourier transform with respect to them. let's denote it as this thing. So what about the analytic structure of this thing? So I will just quote the result here. So people who are interested, they can actually check. This is elaborately discussed in. So this is elaborately discussed in reference. And the result is that in general, there will be poles in the n-dimensional this is n-dimensional space. So in this n-dimensional frequency space, and it is not necessary the pole will be just in omega 1 or omega 2. I mean, the pole can have, there can be poles in, for example, there can be poles in, let's say, poles of this form. Let's say there is a bunch of them. So N, P, Q. There can be pole in subset of them. Okay, so just to be precise, for example, let's say there is a pole in omega 1 plus omega 2 dot 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 omega q square. And then let's say the pole is, the pole again will be controlled by some En minus E0. Okay, and the residue is simply the overlap is simply given by, so if there is omega 1 to omega q, then this residue will be controlled by OT1 dot 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 OTQ overlap with n, and then you just take Fourier transform with respect to dt1 okay. So the residue will be controlled by this lower point function. So the residue is controlled by this q point function, and the pole is controlled by, you see that there is just n appearing here, and the n also appears here. Okay, so you see this. In the for the particular case of n equal this small n equal to 2 is the Callan-Lemon representation. Okay, and what happened in the Callan-Lemon spectral representation? That we found that the residue is controlled by some 1 point function, right? So if we had initially focused on 2 point function, then the residue is controlled by some sort of 1 point function, some mod square of 1 point function. So in this case, what will happen is that if we focus on n point function, then the residue is controlled by some Q point function and n minus, so controlled by product of Q point function and n minus Q point function. Okay, so for example, when for this particular case of n equals to 2, the residue was controlled by 1 point function and 1 point function, right? So in this case, of course, the Q is not equal to 0 and Q is less than n. Okay. So this is the meaning of the pole of the, so if we had look at general correlator, that the correlator will in general have pole on some subset of these variables. And the residue at, okay, good. So pole will be on some subset of variables. Let's summarize. So poles, there will be poles in some subset of frequency space variables. Two, the location of the poles are again the location of the poles are again some En minus E0, and C, the residue at those poles are controlled by product of Q point and n minus Q point function, where Q is greater than 0 and less than n. Okay, so this gives some physical meaning of the correlators, because that means that if we just compute correlators, so what is the advantage? If we just compute all possible correlators, go to the frequency space expression, and look at the poles. Then we know the spectrum of the theory. Okay, so this kind of provides us a rational or a physical meaning of the series of correlators that we have been computing, because now if we know how to compute the correlators, and then if we go to the frequency space, then the pole at the frequency space expressions tells us about the spectrum of the theory. Okay, so later when we go to interacting theory and other theories, we will find many application of this nice result. Okay, and I encourage you to check this for different correlators by explicitly computing them in the free theory.